So welcome to this class. In this session, we are going to introduce the concept of partial derivatives. So give the definition and then do some examples to illustrate how to carry out a partial differentiation. So partial derivatives. So partial differentiation. So let's start by defining what we mean by a partial derivative of a function. So definition of partial derivative. So we say that the partial derivative of a function. So let f of x comma y be a function of two variables. X and y. The partial derivative of f with respect to x is another function denoted by partial f partial x, or you can write it as f sub x given by limit this function partial f so partial f partial x is given by limit as h approaches 0 f of x plus h comma y minus f of x comma y divided by h, provided that this limit exists. So this is the definition of the partial derivative of the function f with respect to x. Similarly, the partial derivative of f of xy with respect to y is another function denoted by partial f partial y, or we can write it as f sub y given by partial f partial y equals to limit as h approaches 0 of f of x comma y plus h minus f of x comma y divided by h, provided that this limit exists. So this is the definition of the partial derivative of a function f of x, y with respect to y. Now, what we call partial differentiation is now the process of finding these partial derivatives. The process of finding the partial derivatives of a function of more than one variable is called partial differentiation. So those are the definitions. Now we can also define the partial derivative of a function of two variables x and y at a specific point AB. So let's say partial derivative at a point AB. So we say that the partial derivative of a function f of x comma y at a point AB is given by, we write partial f. So partial derivative of f of x with respect to x at a point AB is given by partial f partial x. And then you write this line, AB is given by limit as h approaches 0 of f a plus h comma b minus f of a comma b divided by h. And then you add the condition, provided that the limit exists. So provided that the limit given the definition exists. So this is the definition of partial derivative of a function f of x, y at a specific point a, b. Similarly, the partial derivative of f of x, y, x comma y, with respect to y at a point AB is given by so we write partial f partial y at AB is given by limit as h approaches 0 of f a comma b plus h minus f of a comma b divided by h, provided that this limit exists. So this is the definition of the partial derivative of a function f of x, y at a specific point AB. So similarly, you can give the definition of partial derivative of a function with respect to x. If we have, say, a function x, y, z, a function is defined for 3 variables. So you can say we can also define partial derivatives of functions of more than 2 variables in a similar manner. E.g., if we have a function of 3 variables, f of x, y, and z, then the partial derivative of the function with respect to x is given by partial f, partial x, and this defined as limit as h approaches 0 of f x plus h, comma y, comma z, minus f of x, y, z over h provided the limit exists. Similarly, partial f partial y will be limit as h approaches 0 of now f x comma y plus h comma z minus f of x y z divided by h, provided the limit exists, and partial f partial z will be limit as h approaches 0 of f of x comma y comma z plus h minus partial minus f of x y z divided by h. You say provided that this limit exists. So in these definitions, one key thing that you have to remember is that if you're defining partial f partial x, then x is taken to be a variable, and any other variable in that function is assumed to be constant when you're differentiating with respect to x. And when you're differentiating partially with respect to y, only y is taken to be the variable, and any other variable apart from y is assumed to be a constant. Similarly, if you are getting partial derivative of the function with respect to z, only z is taken to be the variable, and other variables in that given function are assumed to be constant. And when you are asked to find partial derivative of a function, and you use these definitions to give the answer, then we say that you are finding the partial derivative by first principle. So note that point. When we evaluate partial derivatives, using the above definitions, then we say that we are partially differentiating from definition or by first principle. So that's what we say when we find the partial derivatives using all the definitions we have given, or using all the definitions we have given, we say we are differentiating partially with respect, partially by first principle or from definition. So in the next session, we'll give examples on how to carry out partial differentiation of functions from first principle to see how we carry out that operation. And remember, the word partial differentiation is because when you are differentiating a function of several variables, say with respect to x, you are only assuming that the variable is x at that point, and then all other variables are assumed to be constant. It's like you are actually doing parts. The function is defined by more than one variable, but as we do the differentiation, we are only considering one variable at a time. So that explains the term partial differentiation. So thank you, and in the next session, I will now describe how we can carry out this partial differentiation from first principle.